This week our notes involve finding complex roots and complex loci. So the fundamental theorem of algebra states that a polynomial of degree n has n solutions in the complex number system. So that means z cubed equals 8 has 3 solutions, whereas we've been used to the fact that it only has 1. The example that I'm doing for you today is about finding the complex roots of -8. So the equation is z cubed equals -8. Now there's 4 steps that we follow in this process. The first step, as we were doing last week, writing the complex number in polar form. It's important to draw yourself a diagram so that you get the argument correct. You can see from the diagram that the modulus of -8 is 8. Notice it's positive, and the argument is pi. We talked last week about the fact that a complex number has multiple arguments. So what we want to do here is to actually generalize the argument to take into account all those different possible arguments. So we want to add a 2 pi, add a second 2 pi, add a third 2 pi, and so on. To do that, we generalize the argument by adding multiples of 2 pi written as 2k pi. We then want to use De Moivre's theorem. And from last week again, De Moivre's theorem tells me that z to the n is equal to r to the n cis n theta. So applying this to our equation on the left-hand side here, we've got z cubed equals -8. We've written that in polar form, so it becomes 8 cis pi. We generalize the argument. So this becomes 8 cis pi plus 2k pi. And then applying De Moivre's theorem, this gives us that our 3 values of z will be equal to 8 to the third, the cube root of 8, cis pi plus 2k pi, divided by 3 or multiplied by a third. It's useful to have this argument expression as one single fraction. Then the fourth and final step in this process is to substitute in different values for k, 0, 1, and 2 to generate the required number of solutions. So if we let k equal 0, we have pi plus 0 over 3, so our solution is 2 cis pi over 3. K equals 1, we've got 2 times 1 times pi, so we've got pi plus 2 pi over 3. We can simplify that to 2 cis pi. And our third one, k equals 2. 2 times 2 pi is 4 pi, so we end up with 5 pi over 3. And we can use the principal argument and write that as 2 cis -pi over 3. So our 3 solutions, taking them out of our working and summarizing them, are 2 cis pi over 3, 2 cis pi, and 2 cis 5 pi over 3, or -pi over 3. Now the interesting thing about these complex solutions, when you plot them on the Argand diagram, they are symmetrical about the origin. So the first solution is 2 cis pi over 3. So it's got a modulus of 2 and an argument of pi over 3. The second one has a modulus of 2 and an argument of pi. The third one, a modulus of 2 and an argument of -pi over 3. So you notice that all of these solutions are actually 2 pi over 3 apart. It's 2 pi over 3 because 2 pi is the full circle, divided by 3 because there are 3 equally spaced solutions. Now there's a couple of other videos that I've given you the links to that I suggest you watch, going through this same process. The second thing that we're covering this week is the idea of complex loci. Now a locus is simply a set of points that satisfies a given condition. And for our complex numbers, there are 3 main types of problems that look at different conditions. The first one involves either the real part of Z or the imaginary part of Z. So the question here is to draw the locus of the set of complex numbers where the imaginary part of Z is less than or equal to 2. You need to replace Z with X plus IY so that you can interpret what this condition actually means. Remember that the imaginary part of Z is the coefficient of I, so the imaginary part of Z is Y. So this condition translates to Y is less than or equal to 2. And you can plot that on a set of axes. So you've got the x-axis, the y-axis. You've got the horizontal line, which is the line y equals 2. Because it's less than or equal to, we want to include the line, so it's a solid line, not a dotted line. And then all the points below that line. The second type of problem that we encounter where we're asked about the locus of a set of points involves the modulus. So the question here is draw the locus of the set of points where the modulus of Z equals 3. Again, let Z equal X plus IY. And we know from last week that the modulus of Z using Pythagoras' theorem is the square root of x squared plus y squared. So the condition we've been given is that the modulus of Z equals 3. So that means the square root of x squared plus y squared equals 3. Squaring both sides gives us x squared plus y squared equals 9. Now this represents a circle, center 0, 0, radius 3. The third type of problem is conditions involving the argument. So here we have a question saying, draw the locus of points where the argument of Z equals 2 pi over 3. So again, we need to let Z equal X plus IY. And if we know that the argument of Z equals theta, or theta equals the argument of Z, then we know something about tan theta. We know that tan theta is equal to y over z. This particular result here, you will find one of the questions in the assignment I've set you. You need to interpret what tan theta is in terms of this ratio. This particular question is quite straightforward. Argument of z is 2 pi over 3. So we need to draw a line which is at an angle of 2 pi over 3 to the positive x direction. And the locus is the ray starting at the origin and heading out at an angle of 2 pi over 3. Any complex number, x plus iy, along that line will have an argument of 2 pi over 3. So those are the three situations that you meet involving locus: conditions on the real and imaginary part, conditions on the modulus, and conditions on the argument. You need to interpret those in terms of what it means for the x and y values when you put z equal to x plus iy.